So today we're going to talk about a concept that you probably haven't seen before in any other class, including your physics classes, and that is this concept of a moment. So let me read you the definition of a moment. A moment is when a force is applied to a body, which produces a tendency to rotate about a point that is not on the line of action of the force. So let's go ahead and dissect that statement and see what a moment means. Let's use a wrench as an example. All right, so if I have my wrench here, I use your imagination. You can also call it a little Lego arm, because that's kind of what it looks like. So we have our wrench here, it's tightening some nut or bolt or whatever it's tightening. And if I apply a force to this body, I apply a force to this wrench, right? Because I wanna tighten the bolt or the nut or whatever I'm doing. I apply a force to this wrench. It produces a tendency to rotate, right? That's why we apply the force to the wrench in the first place. It provides this tendency to rotate about a point, right? So in this case, the point we're rotating about is the nut that it's fixed on. A tendency to rotate about a point that is not on the line of action. So the line of action we've talked about a little bit before. It is just the imaginary, invisible axis that the force F sits on. This is the line of action. It is going to be perpendicular to this point. And this perpendicular distance here between the point and the line of action, not necessarily where F is located, but the line of action is going to be this value D. This distance value. So this tendency to rotate is what we call the moment. The moment. We use the symbol M for moment, and usually we have a subscript for it, which is the point we're rotating about. So we might call this point O. And so we might say the moment about O is the force times the perpendicular distance, right? So that is this force here, this F force, times the perpendicular distance. That's how we define a moment in its most basic terms. It's scalar terms. Because a moment can be a vector or it can be a scalar. Just like a force is a vector or a scalar, it can be either. So this is our scalar definition of the moment. This just gives us the magnitude of the moment. And we'll get into a little bit how you do the vector analysis of it, but right now, as we're learning this, we're just going to do scalar analysis first. So this scalar, just the magnitude value of the moment. Now, it might seem kind of familiar to you, this formula, this moment equals force times a distance, because we have seen that before in physics in the work equation or in the torque equation. Torque is one aptitude, one applicability of a moment. But torque and moment kind of mean different things to us as engineers. Torque generally can only be applied perpendicular, but as we go through these moments, we're going to see where a moment can be applied or a force can be applied in a non-perpendicular way. And you can still get a moment from that. But we wouldn't necessarily call that torque. So they are very similar things, but it's just a nomenclature thing that we use from class to class and from place to place as engineers. We think of torque as one very specific scenario of a moment, but they technically have the same equation. They're both a force times a distance. Now, when we're doing this scalar analysis of a moment, there are two ways we can approach it. So let's say we have some vector F, some force floating in space, and we want to find the moment about the origin. So moments are always about a point. You have to select a point or be given a point that you're taking the moment about. So if we're taking a moment about the origin here, there are two ways we can describe this in scalar analysis. One is that we can find the perpendicular distance, right? That's the distance that is going perpendicular to the force, D, and use our moment equation that we just defined, where the moment about the origin equals the force times the distance. Just their values, just their magnitudes, right? So F could be 5 newtons, D could be 5 meters, and we'd end up with a moment of 25 Newton meters. But we can also break it down into its components, where we have our F has a Y component, right? An Fy component, and an Fx component. And we can use the two distances that are perpendicular to those components instead of, if we're not given the distance D, instead of calculating it, we can use these components in this equation. Moment about the origin is going to be the X component of the force times the Y distance, right? So that's this Y distance here, dy, plus the Y component of the force times the X component of the distance. So that X distance would be from the axis out to where Fy is, dx. So we can break it down into components and then just add the two components together. Your X component of your force times your Y distance plus your Y component of the force times your X distance. So remember that your perpendiculars are always what are going together in this, right? So it's these two because they are perpendicular to each other, right? The Fx and dy, Fy and dx, because they are perpendicular to each other. So that's how we find the actual magnitude of the moment. But just like a force has a direction, right? Even though we can find a number that represents the force, a moment also has a direction, just like a force has a direction. And the way we would determine that is through something we call a right-hand rule. And if you've taken a physics class before, you're probably familiar with a few right-hand rules, just a way to kind of determine the direction of something just by looking at your hand, using your hand to help orient yourself in a 3D space. So the way we would determine the direction of a moment by using the right-hand rule is we put our hand in the direction of D. So out from the origin, or from the point we're interested in, out in the direction of D. And then you curl your fingers towards the direction of F. And your thumb is going to be pointing along the moment axis, where the curve of your fingers are going to tell you whether you're pointing in a clockwise or counterclockwise fashion, which is how we define the direction of a moment. Let's write out the ways that we typically write out how we define the direction of a moment. So usually if you find a moment, let's say for example, I have this force F, and I want to take it about the origin. So what I would do is I would point my fingers along D. So my fingers on my right hand, you have to use your right hand to do this or you will get messed up. You lay your fingers down in the direction of D. So if I were to do this, I'm looking at this on the screen, I point my fingers in the direction of D. And then I'm going to curl them towards F, right? So my hand is curling up towards F. And you can see I've got this kind of backward C shape with my thumb pointing out at U, right? So it's pointing out of the page. Thumb is pointing out of the page at U. And it's going in this counterclockwise direction, right? Around the point. You can also, if it helps, I often draw these circles just right along the force. I draw the circle out of the direction of the force around the point, which will help me orient it in space. So this force, if this is D and this is F, we would say the moment here is counterclockwise, right? So we might say counterclockwise. You can also see it notated shorthand as CCW, or even just drawing the picture next to it of the direction we're going in. So in this case, counterclockwise. That kind of looks like a G the way I wrote it, but it's just a circle going counterclockwise. And if we had some force going the other direction, right? Oh, that's not the other direction. Sorry. Let's say it was going up this way, right? So this is my F now. Now, my moment goes in the opposite direction, right? So this moment is going clockwise. I might say clockwise. Moment is clockwise. Or CW. Or just drawing the picture like this. Drawing the clockwise. Those are the ways that we notate the direction of the moment. And we have to notate the direction of the moment because that's how we determine if it's positive or negative. Right? We typically say that counterclockwise is typically the positive direction, and clockwise is usually our negative direction. So just like we had to notate whether our forces were going towards the positive x-axis and y-axis or whether they were going negative, your moments can also be positive or negative, and you have to choose which way is positive and which way is negative. Convention almost always says that counterclockwise is going to be positive. That's usually what we assume is positive. We assume counterclockwise is positive. Just because that's usually our F pointing up, right? So our counterclockwise is positive. So if we were to take, for example, let's look at a system of moments, right? If we had multiple forces, they would give multiple moments added together. So if I had, say I have this, and I have, here's F1, and here's F2, and here is F3. So I would do right-hand rule on each of these to see which ones are positive and which ones are negative if I'm adding them together to get a resultant moment. Right, so a resultant moment, whoops. Sorry, I don't want that. Nope, I don't want that. Moment resultant is just going to be the sum of your F times D values. So in this case, if we were to use this as an example, our first one, our F1, is going counterclockwise, right? So we're going to assume that that's positive. Sometimes you'll even see a notation that says counterclockwise, positive counterclockwise moment. Just like we sometimes for forces, we said, positive arrow in the right direction for F of X, or positive up direction for F of Y. Moments use the same kind of notation. So we're going to assume counterclockwise is positive. And in this case, it would be F1 times the distance from the point we're interested in, right? It's about the origin, we're assuming. D1. So moment F1 times D1. And then notice F2 is going in the opposite direction, right? If I point my fingers in the direction of D, it has to be, it's the direction of D that's perpendicular to the line of action. So here's the line of action. This would be D2, because this is where it would be perpendicular. So here I would have it going in the clockwise direction, right? If I stick my fingers in the direction of D2, it's the other way. Right? Kind of mirrored for me. Nope, it is that way, right? No, it is that way, okay. Towards F2, right? And then curl my fingers in the direction of F2, I get clockwise. So clockwise is negative, right? So minus F2 times D2. And then finally, I have this distance here, perpendicular to F3, this D3. Again, if I curl around where my thumb is the point that we're interested in, right? And I'm curling around, I see F3 around point O here is going to be counterclockwise. So it's going to be plus F3 D3. So that's what determines our signs in a moment. It's not whether the x's and y's are positive necessarily. It's going to be whether it is clockwise or counterclockwise. Okay, so let's take a look at an example. This is just a basic find the moment about each one of these 4 points, A, B, C, and D. So we have this force here. It is a 10 Newton force. Our force right here, acting on this little backwards F-shaped beam. So we have this 10 Newton force, and we want to find the moment about point A. The way we would write that is we would say MA equals the moment about point A. Now, the interesting thing about the moment about point A is that we said that we can't take a moment if the point is on the line of action, right? The point has to not be on the line of action of the force. So if I draw the line of action here, the line of action of the force goes right through point A, which means that the moment about point A is actually 0. There is no moment about a point that goes through the line of action, right? And we can think about that like if you took your wrench and instead of pushing down to rotate it, right? Pushing down to create a downward force causing that rotation, instead you pushed on it. You pushed right on the wrench, pushed it right into the nut. It wouldn't turn, it wouldn't go anywhere, right? All of your force is acting right on the line of action. And so it's feeling the force pushing it this way, but there's no rotational movement about the point where your nut is sitting, right? So if you put, the upwards force or the downwards force, you can see the rotation in my pin. But if I put a straight line of action within the line of action about my point here on the other side, there's no rotation. So the moment, if the point is within the line of action, is just going to be 0. Let's look at the next point then. All right, so that's our point B. Moment about point B. And we said the moment is just F times D. So what is D in this case? Well, it's the perpendicular distance between point B and point A. So that's going to be this distance here, right? The perpendicular distance between B, sorry, not B and A, B and F. The perpendicular distance between B and F. Over here on the side, it labels as 2 meters. So it's going to be 10 newtons times the 2 meter perpendicular distance is 20 Newton meters. But importantly, what is the direction of that, right? So if we do our right-hand rule and we look at it and we say, okay, about point B here, if I did kind of a giant circle around it, what would be the direction? All right, well, this is a counterclockwise circle. So I would call it counterclockwise about point B. Is it frozen? Uh-oh, no, don't save. Sorry. Okay, it is going counterclockwise, so I need to indicate that in my answer. And I'm going to go ahead and just draw the shape. I'm going to say it's 20 Newton meters counterclockwise. That's the moment about point B. How about point C? All right, point C is right here. And it is the perpendicular distance between the force and C. So it's the same distance actually, right? B and C are on the same line. They're both 2 meters away. So MC is going to be the same 10 newtons times 2 meters. 20 Newton meters. But let's check the direction of this one. Right, so are we still going the same? Let's see, if I point in the direction of D and I curl my fingers around, I get this circle forming around point C, right? So I am still going counterclockwise. I'm going to label it, you can use any of the three labels we discussed, right? So this is 20 Newton meters counterclockwise. I could have drawn the arrow circle again. I could have written out counterclockwise. I can write the CCW. Any of those are totally acceptable. And finally, I have point D. So let's look at our point D here. We'll see that it is 1 meter, right? It is this perpendicular distance is this 1 meter down to the force. So MD is going to be 10 newtons times 1 meter. So we'll get 10 Newton meters. And then we check the direction on that one, right? So if we check the direction on this one, now we see this is going actually clockwise, right? About point D. I point my fingers in the direction, right? Point my fingers down in the direction from the point towards the force, and then curl towards the force. I get a clockwise. Sorry, it's a little I'm mirrored. I'm having a little trouble demonstrating, but if you curl, you'll get a counterclockwise, right? You'll get a C shape with your fist. Your fist should be pointing down into the page, and you get a C shape around point D. So this would be clockwise. Now you do have the option to also say negative 10 Newton meters counterclockwise. You can write it that way, but for positive notation, we can just keep it as a positive and then notate which direction. You have to indicate which direction it's going either way, so you might as well make it a positive. All right, let's talk through this one more example. In this example, we have this 500 Newton force kind of floating off in space, and we want to find the moment about P. So remember, there are two ways we can go about this scalar analysis, which one is we can find the perpendicular distance D and do F times D, or we can break it into its X and Y components and multiply those together. So let's kind of talk about just how we would do the FD first. Right, because it's not the distance from P, it's not the distance from P to the end of the vector here. That's not a perpendicular distance. It might kind of look like it in the way that I've drawn it, but to actually find the perpendicular distance, you're going to have to do some slope calculations and some inverting of things. For this example, it's a little bit easier because it is a 45-degree angle, which means I know that if I go, let's see what our total distance is here. So our total distance is 7 in the y direction and 9 in the x direction, is where this point, the origin point, not the origin point, the start point of the vector is. So if I go 1 up and 1 over, right, because it's a 45-degree triangle, it makes that 1, 1 triangle. Go 1 up, 1 over. I get this point that is now 8 meters away, and up 1 is also 8 meters away. Right, so I know that this actually makes a perfect perpendicular line, right? Because 8, 8, I know I get this 45-degree angle here, which intersects perpendicularly with this one that's going at the 45-degree other way. Some of these get really complicated to calculate, so it's not always the best method to try to find this perpendicular distance. In this case, we can find this perpendicular distance. This is 8 squared plus 8 squared, you take the square root of it, right? It's 8 square roots of 2. is the distance here. And so what you end up with is, if you do the moment by this method, moment about p is f times d, you're going to get 500 times 8 square roots of 2, which if I pull my calculator out, I get 800 times 8 times square root 2. The moment about p is 5,657, if I round 57, Newton meters. And what direction is that, right? So I think about what direction it is. I point in the direction of, point my fingers in the direction of D, and then I curl towards, the other way, curl towards in the direction of F, right? And I get this value that is counterclockwise. Counterclockwise. So that's my moment about P. But I had to go through the work of finding that distance D, when instead I could just use the components. So if I were to do this in component form, that is the force in the x direction times the y distance plus the force in the y direction times the x distance. If I think about what all those components are, right, I have the force in the x direction is going to be negative, it's in the negative x direction, right, negative 500 cosine 45. That's our fx. The dy is going to be our y distance here, we said was 7 meters, plus fy, the y component of our force here, is going to be 500 sine 45 multiplied by the x distance, which we found at the beginning was this 9 meters. Right, 9 meters. And that's to this start point, right? That's the distance that we're finding from the point to the start point of the force. That's multiplied by 9. And if I plug that into my calculator, 500 sine 45 times 9 plus 500 cosine 45 times 7, I get 5,657 Newton meters. Now, an important point that I actually messed up here, and I'm seeing where I messed up, is that each of these, the sign is not determined by the x direction or the y direction. The sign here is determined by whether it's a positive or it's a clockwise or counterclockwise moment. So we can see that this force is causing a counterclockwise movement, as well as the y component. The y component is also causing a counterclockwise movement. So since they're both counterclockwise, our answer should be two positive terms added together, right? Just the 500 cosine 45 is 500 sine 45. So it is not dependent, in our scalar analysis, it's not dependent whether the x and the y are actually going towards the positive x or positive y axes. It's dependent on whether the moment that's created by f times d is positive or negative, clockwise or counterclockwise. So either way we do it, whether we break it up by components or whether we do just f times d and go through the work of finding what d is, that perpendicular distance d, this is how we can find the scalar moment, just the magnitude with the clockwise or counterclockwise direction.